function. And this is, and the other important thing is how many arguments that function has. For example, in the case of getThisID, as you guys remember, what you send is a string of the name of the property you're looking for. If it doesn't exist, it doesn't matter, because basically it's trying to resolve that. So it doesn't exist, we will return as this property doesn't exist. But it do it through getThisID. So basically one of the arguments will be our control, because it's a string. In our case, create element as a string. And in the case of delete member name, exactly the same. The name you can see here, blee, is basically a string. So you can send another string, something you control, and then you have one of the arguments of that method our control, with a string or whatever. So once you know exactly all your triggering offsets, now you know for each triggering offset, you know how many parameters you are sending to that function, and then you know which ones are in your control, etc., etc. Now you have to find all the potential objects that you can replace with that original object. And that could be very, very hard to find. It is. But it's possible. There are, in fact, a lot of objects of that size. And that's why at the beginning I said that if you can control what you are freeing, it's better. Because in our case, we were stuck to 28 bytes, which was the tier of interface. But if you can, potentially you can send different stuff, then you have different sizes of those objects to play with. And then you can find way more replacement objects to exploit. So once you find all the list of different objects that you can see here, right, if you do it with IDA, it's very simple. It's just search immediate value, because usually objects are allocated with a fixed value because they're always the same size. So you will see like a push something, then call new or call malloc, whatever. And then at the end, we will see that it's actually creating all the objects. So if you, with IDA, you just search immediate value, you get the list of all the immediate values, and then you just order it by instruction, and you just go to push, and that's pretty simple, and then you find all the push 28. So once you find all the different objects, you need to check the B table. The first thing that you want to avoid is every object that looks exactly like yours. Like if my object is actually doing getThisID, I'm screwed, because getThisID will work as it's supposed to work, and then it doesn't make much sense to me. Basically, I'm replacing an element with another element, and I mean, I couldn't get anything out of that. But there are other types of objects that has the same different methods at the same triggering offsets. And once you find all of that, you need to check all the triggering offsets you have. That's why if you have more triggering offsets, it's better for you. And you have to find out all the arguments of that method and how they use it. Because if you know that, you start combining things and you see like, oh, this argument is the string to getThisID, but in this case, it's being used in order to save some pointers. That's win. That's basically an inflict. So, or it's using that string as an object, and it's actually calling the B table directly from that string. That's another win. So for each element objects, apart from the tier of interface, there is their own object. And it's not an iDispatch related object. iDispatch is the one that we want to ignore, because iDispatch will have getThisID and all the stuff. We want to ignore that. But for each element, and actually not only these are the elements created through create element, but also the elements that you directly write on an HTML has a completely different object too. And I make a nice list. I don't know if you guys can read it, but you can download the slides later. I find out all the different elements. That took me some time, and the different size of each. So like, for example, you can see in 28, I have all these elements which were allocated on the size 28. And that was pretty useful. So once we have all these things together, there are different tricks you can pull. The first one, and I guess this will be the most important, you basically try to abuse with the replacement function. So basically, you check the arguments, you see that is on the argument string is actually using it's being used by jumping to an object or something else, then you call that function and it's going to work. And usually you can change your primitive into like using arguments as a function pointer or as a write for or as an info leak, etc., etc. Actually, what we're probably looking for is an info leak in this or in all the cases. Another trick you can pull is stack swapping. Basically, you find a replacement function that instead of having 4 arguments, which is why, or 3 arguments, which is what getThisID takes, you find one. You find an object which has exactly same triggering offset, a method that has less arguments. So when that returns, you have your stack swap it, like back when you were doing off by 1 on EBP, something like that. So you have the stack swap it, and then if you're lucky, you will get your string pointing to either ESP or EAP, because it's using it as a saved EBP or as a return value, and then you will get control. This is another trick, because obviously in this case we are pretty limited on the triggering offset that you have available. Even though we have like add, release, getThisID, delete member, etc., etc., there are only a few. Usually, for example, add and addRef and release are usually on most of all the objects. Other thing you can do is sometimes you have the B table, which is very, very small. And after that, you have another B table. So you end up jumping in the middle of that B table. That's possible, and I tried and it works. But obviously, that will depend on compilation. So very, very DLL specific. So basically, one of the other tricks that we found is like sometimes it's very, very hard to find different trigger offsets. So what we did is we call it double object replacement, but we couldn't get anything better as a name. But this is how basically our idea is. The idea would be to kind of try to put a second use after free in order to find more triggering functions. This is pure pseudocode, so this is not JavaScript at all. So just in case you were like, yeah, that's not possible in JavaScript. No, this is completely different. Basically, as every use after free, you first have your original object, and then you call set attribute in order to release and free that object. The object was free, but A is still pointing there. That's the whole point of a use after free. And then basically what you do is you find a replacement object which allocates some memory. It has to be the same size. That allocates some memory and replace the original object. And basically we have A now pointing to the object, and obviously B. So what you do basically is you do a delete A in order to actually delete the replacement object. And the idea is that you call a third replacement object that's going to replace what B was supposed to be. And the interesting part is when you actually use B, which is the new replacement object, in order to trigger more stuff. So basically, what we are doing is we are pulling a use after free on B, and B is an object that we know that have more triggering offsets than the original one. And you replace it with a different replacement offset. This is the one that is going to have all the interesting method that will replace number B, and then you actually use the object B in order to trigger the different triggering offsets. So basically B, in our case, that has to be a tier of objects, obviously. So in this way, you can find even more triggering offsets if you are looking for them, because sometimes that's very useful. And you might be even able to even control more arguments and stuff. On a common tier of object, you have only a limited amount of arguments that you control. So finally, there is a last technique, which is based on a LFH modification. Low fragmentation heap on Vista and Windows 7 works in what is called a lazy activation, basically based on how you use it. Is how it will either going to use a free list or it's going to use their own low fragmentation heap structures. That's fact number 3. If you are really interested in low fragmentation heap, you should check out this guy presentation, which is going to be tomorrow at 3:15. He will explain everything that I'm not explaining right now, and even more. So the idea is that if you are, since it's based on lazy allocations, if you find a size which also corresponds to the size you need to replace your object with, you will be able to set up a free list chunk there. And a free list chunk usually have the forward links as the first reward. So forward link usually point to another chunk. So basically, if you have your memory in that free chunk, you will be able to replace the B-table with a pointer to another chunk that you might be able to control. And that will get you a way to modify your B-table. The other way is by using that. This is a quite complex way, but I mean, it's potentially possible to do it. Basically, if you're not doing the free list, you're using low fragmentation heap chunks, and the low fragmentation heap chunks, when they are free, correct me if I'm wrong, it has a short, which is at the beginning of after the headers, and these shorts basically allow you to connect to the other free objects, like in a chain. So as you can see here, in the object here, you have number 1, and in that object here have the offset to the next one, which is 77, right? So if you do, basically it's just a big box of different low fragmentation chunks, and they're all connected by an offset. So you know that the first free available chunk will be the first one, and then the second one will be related on the offset to the next one, which is inside the first free chunk on the low fragmentation heap, and that's how they are connected between each other. So basically the interesting part here is that when you free a chunk which is on the low fragmentation heap, what it's going to do is going to replace the low significant bytes for that object. That's exactly how it looks like. So the interesting part is that the most significant bytes will be the address to a DLL, most likely. So you could potentially find a way to call a function or call your heap spray by doing this trick, which is in a way what they were doing on the pray after free bags, but in a controlled way, because you can kind of predict what this offset to next one. So you can kind of predict what the low significant bytes will be replaced with, or you can actually enforce that. So in that way, when you trigger the B-table, it's going to be pointed to something that you know is going to kind of control it, and it will be calling something inside the beginning of the DLL, and that somehow points to something you control, like a heap rate. So conclusions.